So the difference between differentiability and continuity. So I'll put continuity here. Continuity versus differentiability. Differentiability. Now, it should hopefully not come as the largest shocker that both of these concepts are somewhat related to limits and limiting behavior. And because that's where that direct segue from the order of the way the course worked, we talked about limits first, kind of nailed down this idea of limiting behavior before going into continuity and then before going into differentiability. Here's the reason for that. It's because everything you're going to find with derivatives to some extent comes from what we know about limits. So because a derivative is defined, it's the very definition of a limit. Or sorry, I got that backwards. The very definition of a derivative is just a specific kind of what? A specific kind of limit. So limits are very, very intertwined with things as we go forward. So to clarify, so continuity is we have a few conditions. We need the function to exist. And I am aware that I have gone over this already several times throughout the different recordings. But the reason for that is just it's so important. Even after Calc 1, even after Calc 2, and even Calc 3. These three conditions really pervade a lot of higher mathematics. So it's good to review them. X approaches A of f of x that needs to exist. So there's where the limits come in as a concept. And then we want the limit to coincide with the function value. So visually, it's basically like substituting A in for x. That's continuity. Now, here's where differentiability comes in. So differentiability is about the limit. So it's a little bit different set of characteristics here. The first thing we need to establish is that the definition of a derivative, so f prime of x, the way we define this is through the use of a limit. So we say the limit as h goes to 0. And then what we're going to do is we're going to essentially put the slope of a line in here. So it's going to be x plus h minus f of x all over h. Now there is technically an alternate form. So if you want the derivative at a specific point, so like more similar to what we were doing over here with continuity, f prime of a, so if I want to find the derivative, the slope of a function at specifically like x is equal to a, then I would take this limit instead. I take the limit as x approaches my point a of, again, it's when you really look at it, aside from all the other jargon around it, it's just the slope of a line. So we have f of x minus f of a over x minus a. This is just the slope of a line. In the same way that if you were given 2 points, x1, y1, and x2, y2, if you were asked to find the slope between them, you would do, well, okay, my rise over my run. y2 minus y1 over x2 minus x1. That's exactly what this is. We are just giving different symbols to it, where the f, so the function corresponds to that vertical component, so the y's. So this is like y2, and this is like y1. So you're taking the difference to see what your rise is. And then in the denominator, you're looking at the run. Here's the x value. Here's the one that you're coming from, and here's the value that you're approaching. And so it's that difference, x2 minus x1. So all you're doing with derivatives is you're taking a super buff of linear, of like your basic algebra and the equation of a line. And you're taking the concept of the slope of your line and now seeing what happens when we start applying the limits to limiting behavior to these slopes. So with that being said, here's where the difference comes. Is that differentiability at a point involves the existence of these limits. So in order to be differentiable at x equals a, this limit needs to exist. So I would say that we would be differentiable at, differentiable at x equals a, if and only if, that's what that symbol means, it's like a double implication, if and only if this limit exists. So it's that equation of a, or not the equation of a line, the slope formula, but put into limit form, that needs to exist. So this exists. So that's really, so from a definitional point of view, here's the differences. To be continuous at a point, you need to satisfy this. That's kind of the crux of the matter. You got to show that the limit as x approaches your point of the function is simply approaching the function value, the what it's defined to be. That's different than this condition over here. We would be differentiable now talking about this, where we need to have.
So it's not the individual limits existing, it's the whole derivative existing.
Exactly. That slope needs to exist, and that slope happens to be defined by a limit. So at the end of the day, when you're checking for continuity and you're checking for differentiability, you are you're looking at limits. For both concepts, you're looking at limits because limits are that's the language for both of these ideas. But the kind of limit that you're testing is going to be different. So over here with continuity, you're just seeing whether or not this correspondence is true, whereas with the slope, the differentiability, you're looking to see if the slope, you're going to approach the same slope from both sides. So let me actually show you a quick visual thing, because that's a lot of theory. So here is a visual representation of continuity at x equals a. So let's make this a. And then I can make a function or something. So here is f of a. And the reason why we would have continuity here, what we're really checking is we're checking that the function from the left is approaching the same thing from the right. And then not only is it approaching the same thing, but then what the actual function is defined to be is indeed f of a. So this is continuity at that point x is equal to a. We've got this left side of the limit in red, the right side of the limit in green, and then in blue, that's how the function is defined. Here's the difference. Continuity has to deal with the actual explicit function values. Differentiability is a little different. We're actually looking more at the slope of a function. So let me just make a parabola here, because those are nice. So let's choose a point, and let's call it A. So I'll mark that point right here. Now, the question is going to be, what is the slope approaching as we get closer to this point? Now, that's a different question than what the function value is approaching. We're no longer talking about the actual function values of this parabola. We're instead looking at its behavior. How much is it changing by? How steep or shallow is the slope on this parabola? And so coming from the left, if I have a point right here, we have a slope like this, and as I bring the slope closer in, we notice that the slope is approaching something that looks kind of like that. So as we bring this second point in and look at what happens to the slope, we start to get closer to a certain value. And if we do the same thing from the right, so that secant looks like that, but as I bring this point in closer and closer, notice that the slope is actually approaching the same thing. So in other words, the function is approaching the same exact level of steepness if you're approaching it from the left side as you're approaching it from the right side. And it doesn't matter which direction you're coming from, that level of steepness is going to get to the same exact thing. So that's the difference. This is differentiability. Differentiability at x equals a. Now, here is the relationship because there is a connection, but it's only a one-way street. Differentiability implies continuity. So if I were to put this down here, I would say that differentiability implies continuity. Where this symbol right here means implies. Continuity does not imply differentiability. So you can't go the other way around. So the other statement doesn't work. You can't say that something continuous is going to be differentiable. You can't say that. But if you have shown that something is differentiable, or if you're told that something is differentiable at a point, then it's implied that then it's also continuous at the point. So there is a relationship between those two things, but it's a one-way street and a one-way street only. So don't get the direction confused. Make sure that it's always differentiability that's implying continuity and not the other way around. Does that make sense?
Yes, thank you.
Awesome.